Have you ever wondered how an AI can just write a poem or a piece of code? It's not magic. It's an incredible piece of engineering called a decoder. And today, we're going to pop the hood and see exactly how these things are trained, how they go from a blank slate to a machine that can truly master language. So here's our game plan. We'll start with the decoder's one and only training goal, which is way simpler than you might think. Then we'll see how it learns the basic rules of language, like word order. From there, we'll dive into how it learns to focus, uncover a really subtle flaw in that system, and then reveal a super elegant fix called stable mask before we look at the pretty amazing result. Okay, so to really get this, we have to start at the absolute beginning. You have to think of the decoder as a musician who's learning to improvise. During its entire training, its world revolves around one single critical task. So this musician isn't trying to compose a whole symphony. Nope. Its only job is to be given a sequence of notes, like do, re, mi, fa, and then guess the one single note that comes next. That's it. Every complex skill it ever develops, from writing essays to generating code, all starts from mastering this one simple game of what comes next. But how does our musician actually get better? Well, it learns by being corrected. Every time it guesses the next note wrong, it gets what's called a loss signal, basically a score for how off-key it was. Then, through a process called backpropagation, it traces that error backward through its own neural network to figure out why it messed up. It's like the musician thinking, okay, where did I go wrong? Was it my timing, my fingering? So it can nail it the next time around. Right, so predicting the next word is key, but just knowing the words themselves isn't enough. The order of those words is everything. And this brings us to a really fundamental challenge, giving the decoder a sense of place for every single word in a sentence. I mean, think about it. Dog bites man, and man bites dog use the exact same three words, but the order completely flips the meaning. Without a way to track the sequence, a sentence is just a jumbled bag of words to the model. It has this kind of amnesia where it can't remember what came first, which makes any kind of meaningful prediction totally impossible. The solution to this is super clever. It's called positional encoding. You can think of it like adding a unique page number and line number to every single word in a book. This extra bit of data gets bundled with the word's meaning, telling the decoder its exact address in the sentence, position 1, position 2, and so on. Now our musician doesn't just hear the note, it knows it's the fifth note in the third bar. Okay, so the model knows the words, and it knows their order, but language is messy. In a long paragraph, not every previous word is equally important for predicting the next one. So now, the decoder needs to learn the art of focus. It has to figure out which words actually matter. And this is handled by a beautiful mechanism called self-attention. Imagine the model is a chef trying to perfect a sauce. To decide on the next ingredient, the chef, our current word, sends out a query. It's basically asking, what flavors do I need to work with? Then it tastes all the previous ingredients already in the pot. Those are the keys, to see which ones are most relevant to the flavor profile it's trying to create right now. Now, there is one absolutely critical rule during training: no cheating. This is where causal masking comes in. It's a strict no spoilers rule. To force the model to actually learn how to predict, it's effectively blindfolded from seeing any words that come after the one it's currently trying to guess. Our chef can only taste what's already in the pot. They're not allowed to peek at the final recipe. And this slide visualizes that rule perfectly. This is called an attention matrix. That colored triangle on the bottom is the past, all the words the model is allowed to look at. And that big, sharp, white triangle on top, that's the future, completely whited out by the causal mask. It's enforcing that no cheating rule perfectly. But even with this incredibly clever system of rules, researchers started to find some subtle cracks in the foundation. This discovery led to what they called an attention dilemma, revealing two hidden problems that were lurking in the architecture. And the paper that really brought this to light, the one that inspires this explainer, is called Stable Mask. It pinpointed two specific weak links in the chain, two little problems that were actually holding back the decoder's true potential in a big way. So here are the two flaws. First, disproportional attention. The math behind the attention mechanism basically forces our chef to pay attention to something that's already in the pot, even if none of it is relevant to the next step. It's like being forced to say the salt is super important when really you just need to move on. Second, there's positional blindness. In a really long recipe, a model can lose track of whether it's on page 5 or page 500. It knows its immediate neighbors, but it can lose its sense of absolute location. So how do you fix these two tricky problems? Well, this is where stable mask comes in. And what's so cool about it is that it's a smarter, parameter-free solution. It doesn't require bolting on some new, complicated part to the model. The researchers behind it essentially asked this exact question. And the answer wasn't to add something new, but to cleverly modify something that was already there, that causal mask, the no spoilers rule itself. The solution is just brilliant. Stable mask gives the model an option to be neutral. So instead of that hard wall blocking off the future, stable mask fills that forbidden zone with a predictable, fading pattern of fake or pseudo-attention scores. This gives our chef an out. If none of the past ingredients are relevant, instead of being forced to focus on the salt, it can divert its attention to this neutral, predictable pattern, effectively ignoring everything. And this slide shows the trick perfectly. The standard mask on the left is just a hard block. But on the right, you can see stable mask fills that blocked area with those predictable, steadily decreasing fake scores. This simple tweak not only gives the model a place to divert its attention, but as a bonus, that predictable fading pattern acts like a ruler, giving the model a constant reference for its absolute position. It solves both problems in one elegant move. So let's just walk through the process real quick. 1, the model calculates attention scores for past words, just like normal. 2, stable masks adds its fading pseudo scores into that future, masked off area. 3, the Softmax function is applied across both the real scores from the past and the fake scores from the future, allowing attention to be distributed. And finally, a second mask comes in and zeroes out those fake scores, making absolutely sure no information from the future ever leaks through. It's a really slick bit of procedural magic. So, that's the theory. It all sounds great, right? But what does this clever change actually achieve in practice? This brings us to the training payoff. And the results? Well, they're pretty striking. First, let's look at that positional blindness problem. This chart shows how accurately different models can identify a word's absolute position. Just look at stable mask. That's the green bar labeled SM. It's hitting near 100% accuracy, just blowing past all the other common methods. Problem completely solved. And this chart shows the second payoff. This is a measure called perplexity. All you need to know is that for language models, a lower score is better. You can see the baseline model on the left and the model with stable mask on the right. The score is consistently lower. This is hard data showing that the model got quantifiably better at its one core job, predicting the next word. So when you put it all together, the impact is crystal clear. Stable mask fixes the weird forced attention flaw. It solves positional blindness, and it directly improves the model's core performance. But maybe the most impressive part is that it does all this for free. No new complex parts to train, it's easy to integrate, and it even helps models handle longer and longer texts. It's a win-win-win. And that leaves us with a really fascinating thought. If such a simple, elegant tweak to a fundamental rule of the game can unlock this much performance, it really makes you wonder, right? What other basic assumptions that we make in AI are just sitting there, waiting to be challenged? It shows that sometimes the biggest breakthroughs don't come from building something bigger, but from simply refining the rules of the game we're already playing.